Alright, this is homework, chapter 5, physics 202. First of this, just find the direction of the force on a proton moving through the magnetic fields in this figure, and then a repeat, assuming the particle is an electron. Remember, our force is given by the cross product, QV cross B. And so we're going to let our fingers go in the direction of the first vector. They're going to fold towards the second vector, and then our thumb will give the third vector. We've done this in class. And this is just for your practice. I'm just going to give you the answers. For this first one, the force is out of the page. Here, the force is to the right. Here, or excuse me, to the left. The force is to the left. Here also, the force is to the left. Here, the force is up. And here, the force is out of the page. Now, for part B, you just take the opposite direction of each for a negatively charged particle. All right. Find the direction of the magnetic field acting on the positively charged particle. So here, instead of finding the force, you're trying to find the magnetic field. So we've done examples like this in class. I'm just going to give you the answers so that you can practice on your own. Magnetic field on this one is into the page. Here, the magnetic field is up. And here, the magnetic field is to the right. I'm going to determine the initial direction of the deflection of these charged particles as they enter the magnetic fields as shown. Here, the force on this particle is into the page. Notice that the particle is negatively charged. So use your right-hand rule. You'll find that the force is out of the page, and then you recognize that it's a negatively charged particle, and so it's opposite that. This particle is going to bend into the page away from you. On this one, the force is in this direction, and so the initial deflection it's going to bend like that. Down here, the force is in this direction when it goes through the magnetic field, and so it's going to follow a path that looks like that. And here, where they're anti-parallel, the velocity and the magnetic field vectors, the force is 0. There is no force. And so it's just going to travel straight through the magnetic field unchanged. Okay, an electron moves with this velocity through a uniform magnetic field. Find the magnetic force on the particle. My force is the cross product, Q times V cross B. And so I just need to find the cross product of these. That's an electron. I'll just leave that as Q for now. 5I plus 3.2K. Crossed with my magnetic field 9.4I plus 6.7J. Making sure to get the order V and B in the right order because B cross V is not the same as V cross B. It's actually the negative of it. Alright, now I want to take this cross product. I'm going to have 5 times 9.4. I cross I. I'm just doing FOIL, so that's first. Outer is 5 times 6.7. I cross J. Inner is 3.2, 9.4. That's K cross I. And then last is 3.2, 6.7. Times K cross J. All right, now some of these go away, actually just one of them. I cross I is equal to 0 because they're in the same direction. And the cross product of parallel or anti-parallel vectors is 0. And then I like to draw my coordinate system up here, and then you can use your right-hand rule to figure out the direction of these other cross products. I cross j is equal to positive k. K cross I, fingers in the direction of k, fold towards I. That's equal to j. And then k cross j is negative I. So if I do this, I get equals to q times 33.5 k plus 30.1 j minus 21.4 I. Now I multiply it by q. Remember, q is an electron, so it's negative 1.6 times 10 to the minus 19. And that'll give me my net force, my magnetic force, rather. It's going to be 3.4 times 10 to the minus 18 I. Minus 4.8 times 10 to the minus 18 j minus 5.4 times 10 to the minus 18 k. That's in newtons. That's our answer. Now I also want to know what is the electron's velocity after 1 nanosecond. So for part B, I want to know what is its velocity after t equals 1 nanosecond. That's 1 times 10 to the minus 9. I can find its acceleration. It's just F over m. That is F, what I found up in part A, divided by the mass of an electron, which is 9.11 times 10 to the minus 31 kilograms. And that gives me an acceleration, 3.7 times 10 to the 12. I minus 5.3 times 10 to the 12 j minus 5.9 times 10 to the 12 k. And that is in meters per second squared. And then I can find its velocity. Velocity is equal to the initial velocity plus the acceleration times the time. My initial velocity is 5I plus 3.2 k. Plus my acceleration times my time. So that's going to be 1 times 10 to the negative 9 times each of these. So it's I'm going to skip this out. I'm just multiplying the time times these terms. So it's going to be 3.7 times 10 to the third I minus 5.3 times 10 to the third j minus 5.9 times 10 to the third k. This is all in meters per second. Now I just combine my IJK terms. The initial velocity was so much smaller than the final velocity that is basically not relevant. But I'll go ahead and include it here. Let's see, this is going to be 3705 in the I direction minus 5300 in the J direction minus what's 5897 in the K direction. And that's in meters per second. A 1.4 microcoulomb charge is moving at 185 meters per second, experiences a magnetic field given here. Notice it's in micronewtons, in a magnetic field given here in millitesla. Find the angle between the particle's velocity and the magnetic field. All right, well, I know that the force is Q times the cross product of V and B. All right, but the definition of a cross product gives me the magnitudes of these. QVB times the sine of the angle between them. And I want to know that angle theta. So theta then is the inverse sine of F over QVB. So I just need to know what are the magnitudes of the force and the magnetic field. I already have the magnitude of the velocity. So I'm going to find those magnitudes over here. Magnitude of the force using the Pythagorean theorem is 2.5 squared plus 7 squared. That gives me a magnitude of 7.4 micronewtons. 7.4 times 10 to the minus 6 newtons. And then the magnetic field is 42 squared plus 15 squared. That gives me a magnitude of 45 millitesla, which is equal to 0.045 Tesla, just moving the place over 3, decimal over 3 places. All right, so now I just put those values in here. The inverse sine of F, which is 7.4 times 10 to the minus 6 newtons, divided by Q, which is 1.4 times 10 to the minus 6 coulombs, V, which was 185, and B, which is 0.045. Putting that in, I find the angle is 39 degrees. 39 degrees. Okay, have this wire is bent into a rectangle as shown in this figure. The battery and resistor connected as shown. And then this wire goes into a magnetic field, and I want to know what is the magnitude of the net force on the circuit. One thing that's not stated here but should have been in the first edition is that this is the length of the wire, and that length of the wire is equal to 1 meter. So I have a 1 meter length of wire that is going through this magnetic field. It has a certain current through it. I just want to calculate what is the magnitude and the direction of the force on the circuit. This is the concept behind an electric motor. I have a wire. I generate in a magnetic field. I put a current through that wire, and it's going to experience some force, which will cause it to spin. All right, I know that the force is equal to IL cross B, or ILB sine theta. I just want to know the magnitude of the force, and then I'll get the direction just by using the right-hand rule and looking at the direction of the current and the direction of the magnetic field. I already know B, it's 38 millitesla. I need to find the current. I know from Ohm's law that I is equal to V over R. That is 12 over 4, which is 3 amps. So I have 3 amps. The length is 1 meter. B is 38 millitesla. So that's going to be 0.038 Tesla. Times the sine of the angle between them. The angle between B and the wire is 90 degrees, and the sine of 90, of course, is 1. So they just leave that off. So that's 3 times 1 times 0.038. That gives me 0.114 newtons. And I want to know the direction. All right, my current is flowing in this direction. All right, and B is out of the page. So fingers in the direction of I, fold towards B. That my thumb points to the left. So the direction is to the left. That's the answer. A current of 17 milliamps. is maintained in a single circular loop with a circumference of 2 meters. So the circumference magnetic field of 0.8 Tesla is directed parallel to the plane of the loop. What is the magnitude of the torque exerted by the magnetic field on the loop? So I have this loop of wire. I have a certain current that is flowing through that loop, and it sits within a magnetic field. This loop is allowed to spin, and when I put this current through the loop, it experiences a torque which causes it to spin. Right, this is, as I said, this is the idea behind an electric motor, and it's the reverse of an electric generator. I can calculate this torque. It's equal to N, which is the number of turns in the wire, B I times A. N is equal to 1. That's the number of turns of wire. This is just a singular circular loop. B is 0.800 Tesla. I is 0.017 amps. And now for the area, I'm going to do this over here. I know that the circumference is 2 meters. And the circumference is equal to 2 pi times the radius. Right, so that tells me then that the radius is equal to 1 over pi. I just solved that for radius. Now I want to know the area, which is pi r squared. So it's equal to pi times 1 over pi squared. So the area is 1 over pi. I'm going to put that in over here. 1 over pi. Now if I want to calculate the torque, I find that the torque is 4.3 times 10 to the minus 3. Since this is torque, it's in Newton meters. A proton moves freely in a circular path perpendicular to a constant magnetic field. It takes 2 seconds to complete 1 revolution. Determine the magnetic field of the magnitude of the magnetic field. First, just write down what we know. The period of this is 2 times 10 to the minus 6 seconds, 2 microseconds. It's a proton, so I know its charge. I also know its mass. And I want to know what is the magnetic field. All right. If I have this charge that's moving in a circular path, I know that there has to be a centripetal force. I know that the centripetal force is mv squared over r. That centripetal force is being provided for by the magnetic force. So the mv squared over r is equal then to qvb. I'm looking for b. This is like we did last semester, by the way. You have the car going around the curve. The centripetal force is provided by the static frictional force. But here, instead of the static frictional force, it's provided by the magnetic force. I just solve for b. B is equal to mv over qr. I don't have v though, so I need to go over here and I'm going to find v. I know that v is equal to distance over time. My speed is distance over time. The distance that it travels in one period is equal to the circumference. That's equal to 2 pi r over the period. So that's its speed. So I can plug that in over here. I'm going to do that. So b then is equal to m 2 pi r over qr times t. Then the r's cancel. I don't know them anyway. And I can solve now for b because I have everything else. It's going to be 1.67. It's the mass of the proton. I'm going to leave off the negative because I'm just looking for the magnitude here. And 2 times 10 to the... And that gives me a magnetic field of 0.033 Tesla. All right, determine the direction of the current. We did these in class. You let your thumb go in the direction of the current and your fingers wrap around to give the direction of the magnetic field. I'll just give you the answers. You can practice them on your own. I is up in that direction. Off to the right. These are the same scenarios. The right here and out of the page here. Those are the directions of the current in each of these wires. Electron has initial velocity and a constant acceleration where there are electric and magnetic fields present. If this is your magnetic field, what is the electric field? All right, so the net force, the net force is the vector sum of two forces. Fe, that's the force due to the electric field, plus Fb. So then I can say that Fe is the difference, the vector difference as it may be, of F net minus Fb. So if I find F net and the magnetic force, then I can take the difference in them, and that'll give me my electric force. And if I have my electric force, I can find my electric field. So first let's find the net force. The net force is just the mass times the acceleration. This is going to be 9.11. 10 to the minus 31 kilograms, this mass of an electron, times the acceleration, which is given. And it's in the I direction. Be very careful to keep all of our I's, J's, and K's accounted for. That gives me 2.7 times 10 to the minus 18. That's going to be in the I direction, measured in newtons. So that's my F net. Now, I want to determine FB. FB is equal to QV cross B. So I need to do the cross product. I have the velocity and the magnetic field vectors. It's going to be Q times 10,000 J plus 13,000 K. Crossed with 400 times 10 to the minus 6 I. It's my magnetic field vector, 400 microtesla. Doing that cross product as we've done before, it's my charge of an electron. I get 4K minus 5.2J. Which gives me a force vector, a magnetic force vector of 8.3 10 to the minus 19 J minus 6.4 times 10 to the minus 19 K. That's in newtons. Notice that I had this negative here. That's why they switched orders and switched signs. All right, so that's my magnetic force. I have my net force. Now I'll just take the difference of them to find my electric force. So my electric force is going to be F net minus FB. Which is going to equal 2.7, taking the difference in them. That's my electric force. Now, I really want to know my electric field, and I know that my electric field is that force per unit charge, F over Q. This is an electron that we're talking about. And so if I divide by the charge of the electron, negative 1.6 times 10 to the minus 19, I get my electric field of negative 17I plus 5.2J minus 4K, and that's in newtons per coulomb. That's the final answer. All right, a wire has 1 amp of current flowing through it. So my I is 1 amp. The wire's in a magnetic field of 3.2K microtesla. And I want to know what is the force. F is equal to IL cross B. This is very similar to it if you think about our original magnetic force equation, QV cross B. What is Q times V if not I times L? Because I is charge per unit time, and so L is in meters, and so these have the same units. See, coulombs, meters per second. Here I have coulombs per second, meters. So those combinations, those two terms have the same units. So this is basically the same equation, except now I'm constraining my charges to a wire. Now, I need to figure out what is the L vector. My L vector starts here and goes here. So if I can determine the X and Y components, then I'll have that vector. My Y component goes from 5 to negative 1, so it has a length of 6. And my X component goes from 2 to 7, so it has 5, a length of 5. So my vector goes from here, that is negative 6 in the J direction, plus 5 in the I direction. So L then is 5I minus 6J. 5I minus 6J. So now I can do my force. It's going to be 1 amp times L cross B. L is 5I minus 6J. Crossed with B, which is 3.2 times 10 to the minus 6. That's in the K direction. If you do that cross product, you get a negative 1.6 times 10 to the minus 5. That is in the J direction. Excuse me, that should be positive 1.6 times 10 to the minus 5 minus 1.9 times 10 to the minus 5. And that's going to be in the I direction, J cross K. And that's my force. The force on that wire. Very similar to previous problems, it's just you just have to define what is the vector L.